Electricity and Electronics. This is Chapter 8. Complete chapter lessons and review questions. Edited, explained, and narrated by Hector Vladimir. This is Chapter 8. Combination Circuits. Series Parallel Circuits. All material from the textbook Electricity and Electronics by Gerrish, Duggar, and Roberts.
The objectives are to determine the equivalent circuit resistance for a given combination circuit, to determine the voltage drops in a combination circuit, to determine the current values in a combination circuit, to determine the wattage values in a combination circuit,
and
to apply combination circuit
theory to troubleshoot the combination circuit.
Some of the keywords
Discussed
here are combination circuit,
equivalent resistance, and series parallel circuits. 8.1
reducing a complex circuit. When solving a series parallel circuit, often called a combination circuit, you will use
all of the formulas
and techniques that you learned in Chapter 6 and 7. When one branch of a parallel circuit has resistors in series, you will use the series circuit formulas to turn those resistors into one equivalent
resistor.
When you come across parallel branches in series with other resistors, you will use your parallel circuit
formulas
to turn those resistors into an equivalent series resistor. The simplest way to understand this process is to work through some examples. 2 examples follow.
Be sure to work through all of these steps.
Reducing to a simple series circuit.
In the first example,
look at the top of figure
8-1.
Shown on your screen. There are 2 8-ohm resistors in parallel.
In series with the 2 8-ohm resistors
is a 5-ohm resistance. To find total resistance for this circuit, we reduce the combination circuit to a simple series circuit. This is done by applying Kirchhoff's law of series and parallel circuits. Using the equal resistances method learned in Chapter 7, you know that 2 8-ohm resistors connected in parallel have a total resistance value
equal to 4 ohms.
This step is shown in the middle of figure 8-1. The combination circuit can be redrawn as a simple series circuit with a new resistor identified as R23. The new resistor, R23, is the equivalent value of R2 and R3 in parallel. The equivalent value of R2 and R3 in parallel is 4 ohms. Once the new resistor, R23, is drawn in series with the 5-ohm resistor, R1, you can see that what is left is a simple series circuit. The resistances in the new series circuit are then added, and the total resistance of 9 ohms is calculated. In the second example, the circuit is just a little more complicated. One more step must be taken when reducing the circuit. In example 2, there are 2 resistors in series in one of the parallel branches. Example 2, look at the top of figure 8-2. This combination circuit has 2 resistors in series together in one branch on the parallel portion of the combination circuit. Again, this combination circuit has 2 resistors in series in one branch of the parallel portion of the combination circuit. These series resistors must be added together before the parallel circuit can be reduced into an equivalent series
resistance.
R2 and R3
can be combined using the series circuit resistance formula
to create an equivalent 12-ohm resistor known as
R23.
Upper right in figure 8-2. Resistor 4, 12 ohms,
is in parallel with
resistor 23,
which is 12 ohms.
When the resistors are combined using the equal resistances
method
for parallel circuits, you create an equivalent resistance of
6 ohms.
This equivalent resistance is noted as R234, bottom of figure
8-2.
All that is left then is a simple series circuit with a total resistance value of
10 ohms.
Reducing to a simple parallel circuit.
A complex circuit can also be reduced to a simple parallel circuit.
Look at the top of figure 8-3. The fastest method of solving this problem is to first combine resistor R1 and R2. This leaves you with a simple parallel circuit that can be solved easily using the product over the sum method or the equal resistances formula. Work through this example on your own. Some review questions for this section, 8.1. First one is to reduce the following circuit to its simplest form. So here we have a circuit that has both parallel and series features, and what we must do is to combine some of the resistors so we can get either a purely series circuit or a purely parallel circuit to simplify things. If at all possible, try to make it a series circuit. If not, make what you can into a series circuit, and what is left
should be a lot simpler. First step is to
write down your problem.
Sometimes
you can draw the circuit if it's not shown. In this case it is shown, but I drew it again on the right side of the screen just to clarify things a little bit. And I named the resistors so we can have a better idea during our computations of what resistor we're talking about. I labeled them. So we have 3 resistors, what appear to be in parallel to the voltage source, R1, R2, and R5. 2 resistors are in between the branches, R3 and R4. So we see right away that we have 3 resistors that are already in series. So we can go ahead and find what that resistance is and combine it. More or less, you can look at it as combining those 3 resistors into one. That way we can simplify the circuit and make it a purely parallel circuit. So
if you
combine those 3 resistors that appear to be in series
on top
and on the right side, since we're going to combine those 3 into the position where R5 is, to make it simple, we can say that R5 equals to R3 plus R4 plus R5.
This is
the series circuit formula for total resistance. In this case, we have 10 ohm resistors for all 3 instances, so we add
10 plus 10 plus 10, which is 30 ohms. So we make
R5 into 30 ohms.
So we can just for now omit the other 2 resistors, which are now
combined into R5, which is 30 ohms. So our resistance total, we can find out,
since
the circuit is now a purely parallel circuit. Now we can use the formula for resistance for
parallel circuits, which is our reciprocal formula. So
we can say our total or resistance total equals to 1 over RT equals to 1 over R1 plus 1 over R2 plus 1 over R3. In this case being 1 over 10 plus 1 over 10 plus 1 over 30. When you add that, you get 7 over 30, or 7 divided 30. However, remember that we must get the reciprocal of that, and the reciprocal of that is
4.28 ohms.
Question number 2 is to reduce the following circuit into its simplest form. Again, we are encountered with a circuit that is not a series circuit nor a parallel circuit, but a combination of the 2.
So
we look for features that we recognize as parallel or
series.
We recognize at the top of the circuit, if you look at the drawing made by hand, resistor 3 and resistor 4 up top, 40 ohms and 40 ohms. That is a parallel circuit. If you see resistor 5 and resistor 6, those 2 are in series, as well as
R1 and R2.
Those are also in series. So there's a number of ways you can go about
solving for this
circuit, and we're just looking to simplify it as much possible.
So
we can begin at the top with R3 and R4,
which is a
parallel circuit. But in this case, I decided to go another route by simplifying the other
series
resistances like R1 and R2. You can combine those as well, but I decided to go with that. R1 and R2 are 25 ohms each. You just add the resistances in a series circuit.
That's 50 ohms.
The other 2 resistances are R3 and R4. Those are a parallel circuit. We can basically
divide, since those are both 40 ohms, they are equal.
We can use the division method for that, where we just take one of the resistances divided by the number of resistors that we're talking about, in this case 2. So 40 divided 2 equals 20 ohms. That part of the circuit is simplified to 20 ohms. Moving on to the next set of steps, we add
resistors
R5 and R6.
10 plus 20 or 30 ohms.
So that's simplified. And we have now a parallel circuit. However, we can
still simplify some more,
like R3 and R4 and R5 and R6. So we can simplify those. In this case, we have 20 ohms and 30 ohms. We add those, we get 50 ohms. So we end up with the circuit that's drawn on your lower right of your screen.
Number 2.
That circuit is the simplified version. So we have 2 resistors of 50 ohms each in parallel. And we can use the division formula where R total equals to R over N, N meaning the number of
resistors that are the same value. So 50 divided 2
we have 25 ohms of resistance
for the
total resistance in the circuit.
8.2.
Solving for voltage and current values. Finding unknown voltages and currents in individual resistors is a little more complicated in combination circuits than it was in simple series or parallel circuits. However, you have just learned the first step in finding those values. Reducing the circuit. Once the combination circuit has been reduced to a simple circuit, the source voltage can be applied
and total circuit current could be determined
using Ohm's law. If the total current is given, the source voltage can be calculated using Ohm's law. Once this information is calculated,
the steps used to reduce the combination circuit could be reversed.
This reversal allows you to determine the individual voltages and the currents through all resistor paths. Once again, the simplest way to learn this process is through examples. Work through the following 2 examples. Be sure to work through all the steps.
Example 3.
And we have those on the screen. Figure 8-4. It shows the same circuit as figure 8-1. But a source voltage of 18 volts has been added
to the circuit.
Using Ohm's law, the total resistance value previously calculated at 9 ohms equals to ET,
which equals
to IT times RT, which in this case, voltage total is 18 equals to current total times 9 ohms. So IT in this case is 2 amps. The total current value of the circuit is 2 amperes. Once the total circuit current value is determined, it can be applied to the simple series circuit to determine the voltage drop values. Remember that the current anywhere in a series circuit is the same. Thus, 2 amperes of current flow through R1 and R23. The voltage drop across R1 is 10 volts, or 2 amps times 5 ohms. The voltage drop across R23 equals to 8 volts, or
2 amps times 4 ohms.
See the upper right circuit of figure 8-4. Reversing the simplification process, R23 is restored to the 2
separate resistors,
R2 and R3. The 8 volt drop is applied to each resistor, as is done in parallel circuit
applications.
Since the voltage drop in each resistor is known, Ohm's law can be applied to find the current values of each remaining resistor. Current 2 equals to voltage 2 divided
resistance 2,
which is the same as current
2
equals to 8 volts divided 8 volts equals to 1 amp. Or current 3 equals to voltage 3 divided
resistance 3,
which is equal to current 3 equals to 8 volts divided 8, which is also 1 amp. R2 and R3 both have current values of 1 ampere. In example 4, the second example, figure 8-5, is based on figure 8-2. The total resistance value of figure 8-2 was calculated in example 2
to be 8 ohms.
The first step is to apply the source voltage of 24 volts to the circuit using Ohm's law. Voltage total equals to current total times resistance total. 24 equals to current total times 10 ohms, and current total equals to 2.4 amps. The total current is 2.4 amperes. The second step applies to the total current of 2.4 amps to the simple series circuit. By applying series circuit principles, voltage R1 equals to current total times resistance 1, and voltage drop at R2, 3, and 4 equals to current total times the resistance at 2, 3, and 4. So
the voltage drop at R1
equals to 2.4 amps times 4 ohms, and voltage drop at 2, 3, 4 equals to 2.4 amps times 6 ohms. So voltage drop at R1 equals 9.6 volts, and the voltage drop at R234 equals 14.4 volts. The voltage drop across R1 has been found to be 9.6 volts. To solve for the voltage drops across R2,
R3,
and R4, you must further reverse the reducing process. The resistor R234
is expanded into resistors
R2, 3, and R4 in step 3. According to the parallel circuit theory, the voltage across R23 and R4 are both equal to ER234, or 14.4 volts. The currents through R23 and R4 can be found using Ohm's law once again. The current at
R23
equals to voltage drop at R23 divided by R23. So the current at R23 equals to 14.4 volts divided 12 ohms, the current at R4, which equals to 1.2 amps, and
the current at
R4 equals to the voltage drop at R4 divided R4, or resistance 4, which is the current at R4 equals to 14.4 volts divided 12 ohms, again equal to 1.2 amps. The final step is to find the voltage
drops
across R2 and R3. Using the current of 1.2 amperes and Ohm's law, the voltage drop at R2 equals to the current at R2
and 3
times the resistance 2. The voltage drop at R2 equals to 1.2 amps in this case times 3 ohms, which equals to 3.6 volts. And the voltage drop at R3 equals to the current at R23 times
resistor 3. So
the voltage drop at R3 equals to 1.2 amps times 9 ohms,
which equals to
10.8 volts. Not every voltage drop in current for each resistor is known. Practice is the only way to ensure understanding of the combination circuits. Always look for 2 or more resistors connected in series or parallel as a starting point for reducing the circuit
to an equivalent resistance.
Once the total circuit has been reduced
to an equivalent series or parallel circuit,
the voltage source can be applied and the total current can be found using Ohm's law. To change each of the equivalent resistances back to their original state, the process is reversed. As this is being accomplished, the principles of series and parallel circuits can be applied to determine the voltage drops and currents. With a little practice, you will master this simple process
and gain an in-depth
understanding of circuit characteristics. This will assist you in dealing with complicated circuits. Power in combination circuit. Power in a combination circuit can be calculated by using either the formula P equals I squared times R, or power equals current squared times resistance, or the formula P equals voltage times current. These formulas can be used for each individual resistance or for the circuit as a whole. Total power in a combination circuit is equal to the sum of the individual wattages, regardless of whether they are connected in series or in parallel. Figure 8-6 illustrates how power is determined in a combination circuit. Review questions for section 8.2.
Question 1. Calculate the total current in the following circuit.
What we want to find is the total current.
So we
simplify the circuit.
From what you see on your screen, on the left you have the circuit redrawn
for clarity, and on the right you have the same circuit
simplified. So to simplify the circuit,
we find the resistance at 1 total. So we find the resistance R1 total. I'm going to name that for the resistance at
the top
of the complex circuit. So that equals to R1 divided
2,
because we have
2
resistors that are the same value. So we can use that
division formula.
In that case, 10 over 2, or 10 ohms divided
2,
which gives us
5 ohms.
Next, we find
R2 total,
which again is
R2
divided
2.
Since we have again equal value resistors, this again is to simplify to make this a series circuit instead of a complex circuit or combination circuit. So
R2 total
is 20
ohms
divided
2, which is 10 ohms. And the third resistor,
R3 total, we have 2 resistors of unequal value.
So
we can use the product over the sum formula or equation, which in this case is 30 times 20 divided by 30 plus 20,
which is 600 over 50,
which in this case is 12 ohms.
So we have simplified our resistors. So
now we solve for this series circuit resistance, since that is the goal.
So
we have resistance total equals to R1 plus R2 plus R3, in this case being 5 plus 10 plus 12 ohms,
which is 27 ohms.
So your resistance total is 27 ohms. Question number 2, what is the value of the
voltage source
in the following circuit? So we're given a circuit without a voltage source, and we want to find out what that is. It's a 2-branch circuit with
2 resistors on each of the branches
of a parallel circuit.
So
we want to simplify
each branch first.
So we have the resistance at branch 1 and the resistance at branch 2. We want to know what those are.
So
to simplify,
resistance
at branch 1, if you want to
follow number 2 on your right side, equals to the resistance at branch 1, that's resistor 1 at branch 1.
The resistor at branch
1, 2.
In this case, we have 20 ohms plus 30 ohms. That's again at branch 1.
Which is 50 ohms.
just a simple addition since we're dealing with resistors in series. We do the same thing for branch 2. The resistor at branch 2 1 plus resistor branch 2 2 equals to 40 ohms plus 60 ohms or 100 ohms total.
So
we have our resistances at each branch of
50 ohms
and
100 ohms. Remember,
those are both now in parallel. We have a purely parallel circuit, and we can go ahead and find out our voltage drop
since we now have
the voltage drop
at branch 2.
And we also have
shown on the problem
the branch current,
which is
all we need to find the branch
voltage drop,
which in this case being a parallel circuit, we know that our voltage drop at branch 1 equals to our source voltage.
So
we go for that. We know if we find out our voltage drop at branch 2,
since
that's where we have our amperage, that would be the same as our voltage source, since voltage is equal to the source
in all branches
of a parallel circuit. We know that by using Kirchhoff's law. So E, or voltage drop at branch 2, equals to
current total times
the resistance at branch 2. We know our current total for that branch, which is 2 amps, and we also have just found out our resistance at that branch 2, which is 2 amps times 100 ohms, and that gives us
200 volts. Since we have 200 volts
at branch 2,
that's the voltage drop at branch 2, so it must be the same as the voltage source.
So we call that our voltage source, and our answer
8.3.
Troubleshooting a combination circuit. Once the electrical concept of combination circuits have been mastered, troubleshooting such a circuit is a relatively easy task. In most cases, taking voltage readings of individual components
is the most convenient
method to use. Look for an open or short circuit condition as indicated by a voltmeter. Troubleshooting a combination circuit uses techniques developed for troubleshooting both series and parallel circuits. The methods used depend on what portion of the circuit is being tested. Look at figure 8-7. In part A, the voltmeter indicates an open circuit at series resistor R1, a voltage reading equal to the source. However, if R2 or R3 is open, you will not see a full voltage reading
across them.
See part B. If R2 or R3 is open, there will still be a complete path for current through the other parallel resistor. To determine if the resistors are open or shorted, the expected voltage drop value must be calculated and compared to the actual voltage drop reading. Look at figure 8-8. Current readings are an excellent way to determine if the circuit components are operating correctly, but this method should be used only as a last resort if it involves desoldering the circuit
to take readings on individual components.
Total resistance can help determine if a circuit is operating correctly, but care must be taken to avoid a false reading caused
by
a component in parallel with another component.
In part A
of figure 8-9,
the
ohm meter is connected across R3. The resistance on the meter value should be equal to only R3. But notice that R2 is connected in parallel with R3. Hence, the resistance value on the meter will be equal
to R2. To take an accurate reading
with an ohm meter, one end of the component
to be read
should be disconnected from the circuit. Part B. To prevent reading other components in the circuit, compare parts A and B of figure 8-9. A component connected in parallel with another component or device in a complex circuit design can be very difficult to detect on a printed circuit board. A false conclusion about the component being tested can be reached easily. A schematic of a complex combination circuit is essential in order to properly identify
which components are connected in series
or parallel with other components. Most electronic systems will have a schematic available.
Good technicians use them
as an integral part of the troubleshooting process. Review questions for 8.3.
The current readings should be used
as a last resort in troubleshooting a combination circuit if what needs
to happen,
and that is
desoldering
could damage components and
complicate
troubleshooting. Number 2, what might cause a false reading when checking a resistance in a combination circuit? And the answer for that is reading components in parallel.
As you may read a good component,
as in schematic
8-9.
The summary for the chapter.
Any complex or
combination circuit
could be reduced to an equivalent resistance or simple circuit after the
total resistance of a combination circuit is reduced to a simple series or parallel circuit. The source voltage can be applied
and the total current value determined.
After total current
is found in a
combination circuit, the original circuit can be reconstructed and individual voltages and currents
can be found
by applying the characteristics of series and parallel circuits. Total power consumed by a combination circuit is equal to the sum of all individual component power consumption wattages. Troubleshooting a combination circuit uses the techniques developed for troubleshooting both series and parallel circuits. Test your knowledge questions for 8.8. The combination circuit can be reduced to a simple parallel or series circuit. Two or more resistances in a combination circuit can be reduced to a series
resistance.
Question 3. Using the circuit
that follows,
solve for the unknown values. This type of circuit is familiar since we worked on one that's almost identical on a previous problem, but we'll follow this one along since there may be a few differences. Again, we are
solving for
the unknown values, which are
on your screen.
They have already been filled in, but we'll work
the
computation so you can see how we went about
finding the answers.
First, we find the resistance at R1, meaning the combined simplified resistance at R1, not necessarily
resistor 1, which we know is 10 ohms. So
the resistances at R1 of this circuit, we can see they are in parallel. How do we find the resistance of a parallel circuit
that has two identical values?
We use the
division formula
for that. R1 divided
2,
which is 10 ohms divided
2,
or 5 ohms. We simplify R2, that's the twin parallel resistors
at
R2. We find that again
because they are the same or of equal value.
We can use the same formula.
Division
of one of the resistances
by the number of resistors.
In this case is 20 ohms divided
2
or 10 ohms. For the third resistor set at the bottom of the circuit, we have two resistors of
different
values. We can use the product over the sum formula, or in this case 20 times 30 divided by 20 plus 30,
which is
600 divided by 50 or 12 ohms.
Next,
we solve for the series
resistance total.
Since we have a circuit, since we have simplified it, is a purely series circuit.
So
we add
those resistances. In this case,
5 plus 10 plus 12 equals
27 ohms. So
next, move on to finding the resistance total. We find the resistance total with
equal
current values. So we need to find our current total. To find our current total, we have to find our resistance total.
So
for that, we use Ohm's law. Current total equals to voltage total
divided by
resistance total. We know our voltage total is given to us 10 volts. So we divide that by our resistance total that we just found out is 27 ohms. And that gives us 0.37 amps. And that is our current total. So we take our current total to find each resistor voltage drop. Since we know in a series circuit, current is equal at each resistor location. So we use that across all of our resistors, which are now simplified. So the voltage drop at R1
equals to
the current total, or 0.37 times 5 ohms, which is 1.85 volts. At resistor 2, the voltage drop at resistor 2, we have
0.37 amps
times 10 ohms, which is 3.7 volts. And the resistance drop at resistor 3 is 0.37 amps times
12 ohms,
or
4.44 volts.
In our next problem, we simplify the circuit again to find the values that are asked for in the problem. There's a variety of values that they want us to find out. Only a few are given. They give us no voltage total, no current at each resistor. They only give us a branch 2 current. And they give us resistor values at each branch.
So
that's all we have to go by right now. If you want to ignore everything that you see in the circuit and just go by what the
problem itself gives us
for now, just so we can work each step of the problem out.
To find each of the values that are supposed to be blank.
So we start by simplifying our circuit branches, branch 1 and branch 2. We're going to call it RB1 for the resistance value at branch 1. which equals to resistance 1
plus
resistance 2. Remember, that's at that branch, R1, branch 1. So RB1 equals to 20 plus 30 in that case. Those values are given to us.
again
We're just adding a series circuit resistance, 20 plus 30 in this case, which is 50 ohms. And we move on to branch 2, RB2 equals to
R1 plus R2,
RB2 equals to 40 plus 60 ohms in this case, or
80 ohms,
we have our two branch resistances of
50 ohms, and
80 ohms. Moving on to the next step, our resistance total. We now have a purely parallel circuit, and we can find our resistance total using our product over the sum formula for resistance. So RB1, which is our resistance at branch 1, times RB2, resistance at branch 2,
divided by
RB1 plus RB2. That is the formula we're going to use. So it's 50 times 100 divided by 50
plus 100, which is 5,000 divided 150,
or 33.33 ohms. The next step
is to find,
our voltage drop at each branch.
since
We have simplified each branch to one resistance value at each branch. We can simply use Ohm's law,
which is
voltage equals current times resistance. But in this case, we call it
the voltage
at branch 2 equals to the current at branch 2 times the resistance at branch 2. In this case, is
2 amps times 100 ohms, or 200 volts. So
the voltage drop at branch 2 equals to,
200 volts.
and we know that in a parallel circuit,
Voltage,
at each branch is the same as your source voltage.
so
Your source voltage must be,
200 volts. And with that,
we can find our,
current total,
which is 200, or the voltage total divided by your resistance total, which we know both of those. We know our voltage total is 200 divided by our resistance total, which is 33.33. That gives us.
6 amps.
So now we have our,
Current total,
since we have our,
current total,
we can figure out one more thing, but we'll leave that for the next step. To figure out the power total,
is found with the power formula,
power or P equals,
E or voltage times I or current.
or power equals voltage times current. In this case, voltage 200. Our current total is 6 amps or 1200 watts. The next step is basically figuring out what our branch current
Is for branch 1, which is the one that's not given,
and we simply
subtract
our
current total,
minus branch 2 current.
and
Whatever's left must be our current at branch 1. So 6,
amps
which is your current total, minus 2 amps, which is the
given,
branch current at branch 2.
which is 4 amps.
So our current at branch 1 must be 4 amps. So we will assume that. We can go further and say, since in a series circuit, the current
Is
equal at each resistance location,
then
we can go ahead and find
each
resistor value with that resistance. So we know in branch 1,
each
resistance at each resistor value must be 4 amps. At branch 2, each resistor location must have,
2 amps each.
so we can find each resistance voltage drop at those locations. We begin with voltage drop at R1, which is the current at B1 times the resistance at 1. In this case is 4 amps times 20 ohms.
Or 80 volts.
We do the same thing with the voltage drop at resistor 2,
Which equals to
the current at B1 times resistor
2,
value, which is 4 amps times 30 ohms.
or 120 volts.
Same thing with the voltage drop at resistor 3, which equals to the current at B2 times the value of R3, or 2 amps times 40 ohms, equals to 80 volts. And lastly, we do the same thing for the voltage drop at resistor 4,
Which equals to
the current at B2 times the resistance value of 4. And we have 2 amps times 60 ohms.
or 120 volts.
We continue with the power at R1. We find that out, which is the voltage drop at R1 times the current at
B1, or 80 volts times 4.
is 320 watts.
Same steps to find the power at
Resistor
2,
which equals to the voltage drop at resistor 2 times the current at B1. In this case, 120
volts
times
4,
amps
or 480 watts. Same steps, same formula used,
for the power at resistor 3,
which equals to
the voltage drop at resistor 3 times the current
at B2,
or
80 volts times 2.
equals to 160 watts.
Same steps,
For the power at resistor 4,
which equals to
the voltage drop at resistor 4 times the current at B2, or 120 volts times 2, or
240 watts.
So the power total is nothing but the addition of each of the powers.
In this case,
we have
4 quantities, 1 at each resistor.
So we have
320 watts
plus
480 watts plus 160 watts
plus
240 watts,
which equals to
1200 watts total, which is our power total.
And that is the end of
the chapter, chapter 8.
Thank you very much.
Chapter 8, Review and Sample Problems by Jerome Barnes. Series parallel circuits or combination circuits.
A combination or series parallel circuit, figure 5.10, is a circuit that will have both a series branch and a parallel branch. You will have to use the rules for series and parallel circuits in this type of circuit. Looking at figure 5-10, the best way to approach it is to find your total circuit resistance first. You can accomplish this by turning parallel circuits into series. R1 equals 50 ohms and R2 equals 250 ohms. You can use the product over the sum method to convert that part of the circuit, which is R1 and 2 equals to R1 times R2 divided by R1 plus R2, which is R1 and R2 equals to 100 times 250 divided by 100 plus 250, which is R1 and R2 equals to 71 ohms. Now you must do the same for the other parallel circuit. R3 and R4 equals to R3 times R4 divided by R3 plus R4. So R3 and R4 is equal to 350 times 200 divided by 350 times 200, which is equal to R3 and R4 equal to 127 ohms. Now add those two together to get the total circuit resistance. 71 plus 127 equals to 198 ohms. The total voltage is already given, so use the Ohm's law formula to find the total current. Ohm's law formula is, in this case, is I equals E divided R, which is I equals 24 volts divided by 188 ohms, which is equal to I equals to 0.121 amps or 121 milliamps. Let's take it a step further to find the voltage and current drop across each individual resistor and leg. This is where you have to pay close attention and use your rules for voltage and current in both a series and parallel circuit. We have all the circuit totals. I equals 0.1218, E or voltage equals 24 volts, and R or resistance equals 198 ohms. We broke the circuit down to two series circuits, R1 and R2, and R3 and R4. We should find the current first because of the rule. We know current will be the same in a series circuit, 0.121 amps in R1 and 2 and 0.121 amps in R3 and 4. With the resistance and the current, we can now find the voltage across ER1 and 2 and ER3 and 4. ER1 and 2 equals to I1 and 2 times R1 and 2. The first leg will be ER1 and 2 equals 0.121 amps times 71 ohms, which equals to 8.6 volts. The second leg will be ER3 and 4 equals to IR3 and 4 times R3 and 4. So ER3 and 4 equals to 0.121 times 198 ohms, which equals to 15.4 volts. Now you can break legs up to find the current drops across each resistor because you know voltage is the same in parallel circuits. Resistor 1 and 2 will see 8.6 volts and resistor 3 and 4 will see 15.4 volts. By using the Ohm's law formula for current, you can find current drops for each individual resistor. IR1 equals to ER1 divided by R1, and so on, with R2, R3, and R4. The numbers may be a little different, but it depends on where you round off. In this figure, I rounded off in 3 places past the decimal point. The answers are ER1 equals 8.6, ER2 equals 8.6, ER3 equals 15.4, ER4 equals 15.4. R1, resistance 1 equals 100 ohms, R2 equals 250, R3 equals 350 ohms, R4 equals 200 ohms. E total equals 24 volts, Current total equals 0.121 amps, and resistance total equals 198 ohms. Current R1 or IR1 equals 0.0860, IR2 equals 0.0344, IR3 equals 0.044, IR4 equals 0.077.
If you want to find power
of each resistor or total power in the previous equation, with all of the total values, current, voltage, and resistance known, set up the formula for power, which is P equals E times I, or P equals
I squared times R.
You must use the values for each resistor if you want to know the power for each resistor, just like you did for current and voltage. Troubleshooting this type of circuit combination can be accomplished with either cold checks, resistance, or with live checks, voltage or current, depending on whether you are trying to isolate the circuit or the components. Figure 5.11. And this is the end of
Chapters 6, 7, and 8 review. Series, parallel, and combination circuits.